Okay, so there was a question on example 5.4 here. I believe this is section 5.4. So actually, it's example 5.40 in section 5.4 of the textbook here. And you're given this triple integral and asked to change the order. So they have it dz dy dx. They want it dx dz dy. Okay, and they do something here, and there's a question about typos, and there definitely is a typo here, but not what was suggested. This is exactly the same order as it was before, dz dy dx, and down here it's dz dy dx. So this z equals y squared should actually be the same as the z equals y right there, matching the description here. Okay, now that being said, we still need to change the order. And I will go through how I do this, which is a little different than the way the book does, but it's equivalent. Right. So here's the integral. So we want to change to the order of dx, dz, dy. So that's what we're aiming for. The way I do this is to draw the region. I want to take a look at it so that I can then see what I need to do. So there's 6 bounding surfaces given by the 6 limits of integration here. So with x on the outside here, this is x equals 0 to x equals 1. So this is the x-axis, the y-axis, the z-axis. So x equals 0 is the yz plane. X equals 1 is a plane parallel to that intersects here at 1. So I'm not drawing it in yet because there's going to be everything behind it. But there's a plane parallel to the to the yz plane out here at x equals 1. Okay. The lower limits here are all 0. So x equals 0 was the yz plane, y equals 0 is the xz plane, and z equals 0 is the xy plane. And since those are all lower bounds on this interval, we're talking about x, y, and z are all positive. So I'm out here in the first octant. Now, the upper bounds, we've already mentioned x is 1. For y, the upper bound is y equals x squared. Well, in the xy plane, y equals x squared is a parabola, right? That goes through the origin. It goes through the point. If this is 1, then this is 1, 1, 1. So there's this parabola. It's also, back on the other side too, but I don't need to worry about that because I'm only interested in positive values of y. Now, so the question of which side are we on? Y on its lowest side is at 0, and on its highest side is at x squared. So I'm looking at stuff down here. So with x between 0 and 1, and y between 0 and that curve, y equals x squared, that's the region we want for y. Now, notice that the y equals x squared is not just that curve, because there's a z involved here, although z is not involved in that equation. So it's actually a cylinder. I call it a cylinder just because you extrude that curve upwards. So the surface that is y equals x squared is a parabolic cylinder. Just slide the parabola parallel to the z-axis up and down. Okay. Now, what does z do? Z is at the smallest 0, so down here at the base, and at most z equals y. Well, z equals y in the yz plane is just the line, right? So in the space, since x is here, but it's not in that equation, then you can extrude that thing parallel to the x-axis, and you get this plane. Right? And so this will go up and hit right there. So it's bounded on the top by that plane. It's bounded on one side by that parabola. So I'm going to, where does the parabolic cylinder there hit the plane? Well, there'd be a curve that would work its way right up to there. So the front side of this, I'm going to redraw it over here. So I got this parabola down here. I got that on the bottom. Let's go up. slide that down there, and then there's this curved side here. Right? So that's the region we're looking at. Okay, that's the region we're looking at. X is going between 0 and 1. That's the outside one. For each value of x in between, y goes from 0 up to x squared. And then for each value of z, z goes from 0 up to wherever it is on that diagonal plane going through there. That's the region. So now, converting that into the other order of integration, still have the same function, but now I'm doing dx, dz, dy. I'm going to start on the outside. Y needs to be, the lowest value of y is 0. The highest value of y right here is 1. For each value of y, the x's, sorry, what's next? Z's. Okay, sorry. For each value of y here, there's a slice that looks like this, and the z's go from the bottom of 0 to the top, which is that plane, so that's just z equals y. And then what does x do? Well, x is at its lowest point, the square root of y. Well, it's on the curve, y equals x squared, so convert that into x equals the square root of y. So the lowest point is the square root of y, and the highest point here is 1. Now let me double check that that's what the book ended up with as well. No, it is not. They have right here a z equals x squared. Right there, they have a z equals x squared, which could not be possibly right. It just could not be right, because they even said before, I mean, in that same line, so I'm looking at, let me slide this over here. So I'm looking at the book's answer here, and they're saying that the middle integral here has to be z is some function of y to some other function of y, and yet they give it as a function of x. It has to be a function of y. Well, the function of y that's bounding z is that diagonal plane z equals y. So this should not be an x squared right here. This should be a y, just a plain old y. Wow. So let's get that out of the way again here. And I am confident with a y right here. Right. The outside integral has to be numbers. The limits on the middle integral can be functions of the outside one. Well, so it can't be a function of x. X is the inside one. It has to be a function of y. That's why I like the y right here. Right. Likewise, the inside integral can be a function, the limits of that can be functions of both the outside variables. So I could have z's and y's in here, but I don't need them. I only need the y. Okay. So anyway, for what it's worth, there's that example 5.40.